What is up, everybody? Isaac here with Civil Engineering Academy. Excited to be with you today. Today's episode of our podcast, I actually bring Mark back on, and we talk about performance-based design and what that is. So, a lot of people in the structural engineering world might be confused what performance-based design actually is. So we have a quick conversation about it. It's not going to be a comprehensive topic discussion, but it's growing in popularity. So I bring Mark on and we talk about it, and it's going to be a good one. So hang around, and it's going to be coming right up after this. All right. What is up, Mark?
Hey, good. I'm doing well. We got a little snow this morning, Isaac. Did you look out the window today?
I did. And my kids want to learn to ski, so I might do a ski thing, but
nice.
It's going to be a zoo. So
nice.
We'll see how it goes.
I got to fire up the snowblower, so it's a good day.
I quickly realized I needed one of those when my back started feeling it. So
yeah.
I guess that happens when I turn 40. Your back starts going out.
Back goes out.
Or maybe it's the kids. I don't know. One or the other. So, Mark, we wanted to talk today quickly about performance-based design and what that's all about. I think before we do that, though, maybe it might be helpful to talk about the history of structural design, maybe up to this point, and how performance-based design even came into play, or just get your thoughts around that.
Yeah.
So, what do you think?
This is a pretty I'll call it a sophisticated subject. You can get pretty deep into down in the weeds on this thing. And Isaac, as you know, I'm not an expert on this subject. I do know a little bit about it, and I can tell you some things. And hopefully for our listeners, this just kind of maybe sparks some interest for those that are interested in structures and learning more about performance-based design, to maybe dig into it a little bit deeper. So
perfect.
We just kind of want to do an overview of what it is and maybe where it's applied. And but yeah, I'd like to start with maybe some history. So structural engineers are very familiar with any good practicing structural engineer is familiar with the codes, right? That dictate. They're very prescriptive.
The code.
Yeah, the code. So we've got our IBC codes, right, which is the prevailing codes. And then we have specific codes that are directed towards the materials that we might be using. So if we've got structural concrete in a design, then obviously we're going with an ACI 318 type code for the prescriptive requirements that are required for structural concrete. And then steel has AISC 360, right? So every industry
laid out, right?
Yeah,
you're going to the code
kind of has
their something.
Yeah, they all have their codes that they fall back on, and so and kind of the history behind that is there was a guy back in the day. I think it was in the 30s, Mr. The Hardy Cross, who incidentally invented the moment distribution method. I don't know if our listeners, that have gone through structural engineering classes. And it's my understanding, I had to go through that. And it's a cool method of solving indeterminate type structures, right? Where you use this method that, and sometimes it's even called the Hardy Cross method because he developed that. Well, he was a smart guy. And what he came out with is this prevailing I'll say concept, or this prevailing thought that structural engineering should be based on standards, which is a good thought. It should be based on standards. It's kind of a best practice, right, for things that actually work, that perform, that can preserve life safety in a structure. If we figure out something works, let's do it, right?
And it gets everybody on the same page.
Yeah, make sure everybody's on the same page. And then let's codify it, right? So let's put it in a book that codifies it, that makes it prescriptive, that everybody can follow the same rules, and then everybody's practicing like they should. And so that was kind of the prevailing thought behind creating the codes that we use today.
Okay. So along comes performance-based design. So what is that and why is it a major topic of conversation these days?
Well, what started happening is, and again, this originated in California because obviously they experience a lot of seismic activity out there, and during kind of the tech explosion, I'm not a historian. I don't know if that's the official name they throw on that event, but during the mid 70s through probably the mid 90s, when the technology, Silicon Valley, the computer technology really started exploding, and companies, and then plus there was a lot of seismic events through that era.
All right.
I've heard that they were as frequent as, like every 18 months or something crazy like that. And I'm old enough that I lived through some of those times. And, that was always kind of the thing is, California gets a lot of earthquakes and you hear about them in the news a lot. And so, um,
Hey,
they,
they're just used to them these days.
yeah, yeah. But what was happening is these owners of these tech companies, their buildings were crumbling, right? When an event would happen and they suffer damage to their building, they'd have to evacuate all of their employees, and then they were suffering economic loss, right? Because they couldn't get all their employees back to work. And so they started demanding the structural engineers tell them if their buildings were going to perform, right, for a given seismic event. We get the next 5.8 magnitude earthquake. What's my building going to do, Mr. Structural Engineer? And most of them are just kind of like, back then were, I don't know, your building's code compliant. That's basically all they could say.
That
And
makes
so
sense.
from that process, also there was some pushback from the insurance industry, the companies that were insuring these buildings, to have something defined as far as how a building would perform. And so I think that was the birthplace of this performance-based design
Okay.
concept.
Um, why does a performance-based design, do you think, why is that a better option sometimes for customers or clients? Why would they want to choose that?
Well, because they have, I mean, primarily we're worried about life safety. That's the primary concern, and that's the base concern with the code prescriptive, requirements on buildings. But sometimes there's additional requirements that owners have that are, I mean, they're economic requirements, or economic needs. They want to use their building after an event. Um, and they want to have some level of assurance that that's going to happen. And so uh, that's when it's used, is when clients are demanding those kind of things. Does that make
So,
sense?
yeah, what there can you walk through like the four levels that usually you have with these performance-based designs, and also where it makes sense to maybe use these in terms of what kind of building you're building.
Yeah. So the built environment. So most buildings, 93% of our buildings that are built are in the 1 to 3 story range, right? So
Hmm.
most homes, most retail places, most businesses, they're in that 93%. Then you start getting into a little bit higher buildings, that get up to about 14 levels. Um, if I go up to 14 levels, that will incorporate like 99% of all the buildings. And
Wow.
then there's like 1% of the buildings that are high rises that are 14 stories or above, um, that that really, I think, benefit the most from this performance-based design approach. All buildings can be designed this way, but it's really the high rises that I think benefit the most from this
So
approach. But
really this falls, I mean, typically this performance-based design comes into play in this 1% of buildings over, real tall buildings.
Yes, it can be applied to others, and again, it's all kind of client based. If clients want an additional level of performance, and we'll go through those real quick, but then it can be applied to any building. But what happens on these high rises is they're subject to more risk, right? So you've got seismic loads, you've got wind loads, you've got a lot more things happening um, to a high rise building than happens on a typical low
Sure,
rise
that
or,
makes sense.
yeah, a smaller structure. And so, um, analyzing the structure and developing these levels of performance actually can be a beneficial thing, and we can talk about that. But
So, like, how is this presented to a customer that's building something like this? Do As an engineering firm, do you say we could go this route or we could go this route? We can go prescriptive, or we can, you choose some of the things you want to meet, and we can match that.
yeah, it's usually the structural engineer understands what type of project it is, right? And then they understand what the client's needs are, and then they can start proposing some of these different things, um, some of these different performance levels.
Got it.
And if we talk about what those are real quick, Isaac, the
Yeah,
performance levels. So the base performance level they call collapse prevention, or CP, and that's basic. Just keep the building standing so it doesn't fall down. This The next one they call life safety performance level. So the building remains standing. It's relatively, structurally, it's still kind of holding together. There's some damage. Excuse me. But
personally, I'm a little confused between those two. If your building's still standing, doesn't it mean you've got life safety?
well, in collapse prevention, you might have some interior elements. Maybe the suspended ceiling is falling on people.
Uh,
Maybe there's some internal, excuse me,
but like,
internal elements of that building that are still falling down and smashing people. The building's going to stay up, but maybe there's some internal elements that aren't going to be so safe
that makes sense.
when the big one hits. So that's collapse prevention. Then there's life safety, which is the next level up in performance. And so again, the building still, it's standing up. There's some damage. Beams are cracked, floors are cracked, whatever's going on. But people are able to get out, and the building is not usable after that. It's suffered enough damage that you can't go back in and occupy it.
All right.
Then there's the next level, which they call immediate occupancy. So there may be some damage to the utilities in this performance level. So maybe the lights won't come on yet. Maybe there's, I don't know, the gas utilities aren't functional quite yet, but people can actually go in and occupy the space without fear that something's still going to fall down and the structure's not going to perform.
Okay.
And then the highest performance level they call is the operational level, where, I mean, it's almost like the earthquake never happened. The lights are still on, mechanical systems still work, the structure is intact. None of the systems, the facade, the perimeter systems, the curtain wall systems, all those are still intact. Then go right back to work, or that building is fully usable after an event.
So I'm just thinking out loud here. That sounds more like hospitals, schools, things of that nature.
Yes. So the risk categories
Yes.
is what you're talking about. So there's risk categories 1 through 4, I believe, in the IBC, and most buildings fall in that risk category 2. And then hospitals get up into the risk category 4, and so yeah.
Didn't you
So
build your house to a risk category 4? I heard. Make sure that thing's solid.
yeah, it would have been a little more expensive than I wanted. I felt like I could take the risk by not going that
Okay.
stringent. Yeah.
That's very helpful to understand those different levels. It almost sounds like they are comparable to risk categories in my mind. But
Yeah.
I can see that
But what
those are,
happens is in the
yeah,
code prescribed scenario, they just bump things up by a factor of safety, right? So if you've got a risk category 1 or 2, your factor is just 1.0. And then if you start getting up into the other risk factors, you start getting into 1.3
makes
and
sense.
higher, where they're just bumping up the structural requirements by a factor. They're not really analyzing the performance, meaning they're not really modeling it, running an earthquake, an actual earthquake acceleration spectra through the model, and actually looking at the response of the building. Right?
Hmm.
They're still just adhering to prescriptive parameters.
I'm just thinking out loud here, but I'm thinking, where is something like this applied to other industries? And as we were talking earlier, we mentioned like fire engineering, maybe doing something that more performance based as to maybe what they want to cover if you had a fire in your building. But I'm also wondering, like, I don't know this, but I'm wondering if it is applied to other industries or even other engineering fields like software or something like that, where you choose kind of which level of performance you want to go and try to reach that.
Yeah, well, they're the higher end structural engineering software programs do accommodate performance-based design now. Um, one specific that I know of is the ETABS, is a specific one, and that's a product by Computers and Structures Inc.
Hmm.
And it actually is geared towards these high rise buildings, which are again in the 1%. And most structural engineers, they never design in that
That
arena.
level.
Yeah. But this software accommodates that, and it's a nice resource for them to have. But I've watched demonstrations of the software where they've modeled a building. The one I saw actually had the lateral seismic force resisting system they called it a ductile reinforced concrete core that actually had coupling beams, they called it, which were over the openings in there. And
Hmm.
they walked through how they modeled that, how they modeled the coupling beams to be a yielding or a non-ductile element in the lateral force design. Excuse me. And then they actually ran the Northridge earthquake accelerations through the model, and they looked at the reaction of the building, how it performed. And what was cool about it, Isaac, and this is what was cool, and I'll tell you a story about when I was involved with a development here in Salt Lake City called the City Creek development. But what was cool about that is they could actually view how the building performed under a real scenario, and that's not the only scenario they could throw through it. Right, that was just an actual acceleration from an actual earthquake from
Hmm.
seismographs that they've actually used to measure accelerations, a real life scenario. And they could see the performance of the building. They could test the strains and the stresses on the core and see how it performed. And rather than just adhering to a prescribed set of rules from the code, they could actually, move reinforcement, and adjust the reinforcement ratios in this core wall,
Hmm.
and actually get a cheaper structure, meaning less steel was required, or less concrete, maybe using a little higher performance concrete, a higher strength concrete versus more mass or more concrete that was maybe of a lower strength. Anyway, the bottom line is they could get a little better efficiency out of the system by actually looking at what was going on, and actually save the owner money in construction costs at the end of the day, because the building was really fine tuned, right? So
That's
they were
awesome.
They were putting the additional steel where it was needed, where they needed ductility, they needed things to yield, they could make adjustments. The coupling beams they could adjust, redesign. They could really target the design rather than just going through and, you know, uh, making everything per
Mm.
the code, which again is very prescriptive. And so
Do
my
you
first exposure to this, I'll just tell you a quick story. Back in this was tell you a little bit about how old I am, but back in 2007, I was involved with I
you're
was with
old.
a structural concrete specialty subcontractor back in those days, and I was part of the design assist team, and we were going in to the structural engineer, which was MKA up in Seattle, and this was back when performance-based design was just kind of cutting edge, and MKA, Magnuson Klemensick and Associates, they're pretty progressive, and they blew me away because they had all of these models. They were actual physical models of the cores that they were going to design. Back then, we called the 32-story residential tower that was part of that City Creek development. They called that Tower One, and they had an actual physical model of Tower One and the core wall system that they were going to design. And they had two systems there. They had actual physical models, and so that you could see the density of the rebar that was to be required if they adhered to the prevailing codes of the
Hmm.
day. And back then, I think we were IBC 2003, I want to say. Um, and then they showed what a performance-based design would yield, and the steel in the shear walls was significantly lighter.
Wow.
And so when I saw that, I was like, "Whoa!" That represents a lot of tonnage of rebar, and it's going to be a huge savings for the owner. Just because they don't have to go through this prescriptive design process.
That
So
makes sense.
it was kind of eye opening to me at that time. That's when I was first exposed to it. But
I mean, so as we drill down to this, it sounds like the biggest benefit to doing this performance-based design is that you actually save money on the construction of this
you,
thing by
yeah, and
not
I would hesitate
needing so much
making that as a
material.
blanket statement. You can. I wouldn't just make that as a blanket statement across all projects, but
You can save money.
you can because you're actually analyzing the performance and you can fine tune it, right?
That's
And
cool.
and there may be areas where you can take material out, maybe you have to add in other areas, but it's a good possibility. Let's just put it that way.
Well, it sounds like you touched on some, I guess, some brief negatives there that maybe you have to add material in other places. Are there any other negatives going this route that you can think of?
Um, well, some of the big negatives is just that it's been around a little while, but it's still kind of cutting edge, especially when you're trying to go uh, and approach municipalities, right, which are in charge of public safety and enforcing provisions that ensure public safety, which includes the building codes, right?
Right.
They're in charge of enforcing those things and making sure that any structure that's built uses those codes in construction. Well, if you throw the code out the window, uh, what's the municipality left to do? What do they have to hang their hat on? They're a little bit worried about that. They get scared.
Yeah, that's definitely an issue I see. Is this even taught in schools? I mean, is this a layer that is taught in schools outside of learning the prescriptive stuff that you're
Yeah,
aware of?
it's taught in schools. It would be more of an upper level, upper
Upper
division type course.
class?
Yeah, it's not. It wouldn't be something that's taught in your base
Makes
engineering
sense.
courses. But yeah, it's an upper level structural dynamics type course. Um,
Are there other resources for anyone that's interested in this topic that they could dive into this a little more that you're aware of?
yeah, there's a few, but I would just go back really quick, Isaac, to the municipality thing. So
Mhm.
when I was involved with that City Creek job, it took quite a while for them to educate the building department to get familiar with what was actually going on. And the performance-based design also took a third-party peer review, which also gave the municipality, in this case it was Salt Lake City, a level of comfort with what design was being developed. So performance-based designs always require a peer review.
Gotcha.
So
I didn't know that.
yeah, they
So
always
I guess
require that.
that's, another possible negative going this route, but it brings a sense of comfort to everybody,
Yeah,
obviously checking this. So that's
yeah.
good to know.
It's just a good idea because we're kind of getting outside the prescriptive parameters. But again, it's just a really cool kind of thing that's it's really interesting to me. And again,
Hmm.
I told you my story about when I first ran into it, and just seeing the efficiencies that can be realized when going this route, and just analyzing buildings with real world data. You're not just going to the code and trying to find prescriptive acceleration and spectra that's in the code.
It's
You're
awesome.
actually running real life accelerations from an earthquake into your model and seeing what your building does. It's just, I don't know, to me that's just kind of a cool thing.
So who's the group that's kind of on the cutting edge of this? Who's publishing stuff that people can check out?
I think Berkeley is kind of the the guys that are on the cutting edge of this, obviously out of California. And there's a lot of progressive, I'd say, structural design firms. I mentioned MKA, Skidmore, Owings and Merrill, SOM is another one. There's a lot of Pacific Coast type engineering firms that are really well versed in this. But
Okay.
but a good resource comes out of what's called the Pacific Earthquake Engineering Research Center, or PEER, PEER. And they publish a guide that's called the Guidelines for Performance-Based Seismic Design of Tall Buildings. And they did that just to kind of give some structure to performance-based design, because it is kind of wild, wild west. At first, it was getting outside the code. And this kind of gives some, I'll call them best practices that engineers should follow as they get into performance-based design. So
we'll link that up in the show notes so people can go check that out. Mark, this has been a fun conversation to have with you, talking about performance-based design. This was actually new to me. It's the first really I dove into this and really started looking into it. So definitely informative to me. Hopefully it is for others, especially in the structural engineering world. So, yeah, thanks for joining me today.
You bet.
All right. We'll see you on the next one.
Okay. See you, man.
Okay. See ya.
Bye.